Welcome. Aloha, biostatisticians. Did you just come for the free candy? Okay, don't eat it until we've collected the data. We have delicious data to collect. So for this lab, let's start by going to our Laulima. Log into your Laulima and go to the assignment. All right, let's go to the assignment lab 6 chi-squared M&M lab. And it has two attachments. There's the chi-squared M&M's lab handout document. Download that. And then the chi-squared M&M's lab code, which is a .r file. So for that to work, it's going to open up like this, a bunch of text in a new tab. Just select all of it, Control A, select all of it, and then go over to R. Open up your R session. And here, what you need to do is go to File, New File, R script, and then just paste all that text into R. Oops. Select all from this tab, copy, go to R, create a new R script, and paste it in. We're not using a notebook this time. And now the wise student decides also to save this as something. So if you click up here on this little save icon, okay, and it'll bring you to where maybe you want to save it. You can save it where you like. I like to keep it in my biostats folder in a little subfolder that has to do with chi-square. Right. Actually, I've already saved it here, but that's it right there. I'm going to overwrite my old one. Save. Yes. Okay, great. So I've got exactly the same thing you have. Okay, I've got exactly the same thing. And then I'm going to go to my downloads folder. And that's where we've got the chi-squared M&M's lab handout. And again, you can save that where you want. I'm just going to open it up from my downloads folder for right now. And if you need to say enable editing, enable editing. If you're not opening it in Word, you open it in this software that works for you. Is everybody with me? That was pretty easy so far, right? For this lab, besides getting to eat delicious M&Ms, we're going to practice the 3 chi-square analyses that we learned about in the lecture on Tuesday. Part 1, we're going to test for equal proportions. Then we'll test in part 2 for expected proportions. And then in part 3, we'll do the two-way test to compare our class data and the data from last semester's class that I've included here for you. And that's mostly where we're going to need to use the R, but we're going to use R all the way through. But here I've actually also given you the code so that you can copy and paste. So this is very similar to the homework, except we're not going to be doing the calculations in class. First, we'll do the chi-squared goodness of fit test to test the hypothesis that there is an equal proportion of M&M colors. There are 6 M&M colors, so we expect that 1/6 of the M&Ms will be blue, 1/6 brown, etc. How would we phrase our question here? You got to type out your question. How do we say this? Something like, are the proportions of M&M colors equal? Right? And then our null hypothesis, 7M, M and M. Our null hypothesis is that, yes, they are equal. So we could say the probability of blue is equal to the proportion of blue is equal to the proportion of green is equal to the proportion of red, etc., etc., which is equal to 1/6, right? Or the alternative hypothesis is that not all proportions are equal. You could also state this as all proportions are equal. Not all proportions are equal. And then you could also state this as probability of blue would just replace all of these with the not equal to sign, which is easy to do in R as this, or you can find it in your insert symbols, not equal to symbol, right? You could put that in there too if you want. Okay, pretty straightforward to state that null and alternative hypotheses. Now we need to actually take some delicious data. If I go back over to Laulima and I look on the resources tab, I find this cool thing over here in under R scripts and data. This is the link to the class data. Click. All right, here is our class data. And in our class data, we now have the colors here. Now these are for the counts of our M&Ms. So each person now gets to open up their pack of M&Ms, count how many candies they have of each color, and enter the data. Enter the data in the spreadsheet. Yay! Finally, I get to open my M&Ms. And you probably can't see the colors. They're a little bit different. They're like kind of more earthy, earth tones. Maybe just because of the humidity. Okay. And also, I don't know if any of you are old enough to remember, but that once upon a time there used to be 2 different color brown M&Ms, and that you guys don't have that, right? There's I have this old fashioned, it's brown and tan that wasn't in. Oh, I think my data are gonna skew everything. Maybe I shouldn't include it. Man, I still get to eat them, right? Let's see, I've got brown, blue, green. I don't have orange. That's what I don't have. I don't have orange. Oh, maybe that's what these tan ones are supposed to be. They're supposed to be orange. Okay, I'm going to count these as orange. It's so weird. Okay. Latin American M&Ms come out looking different colors. You think the humidity's high in Hilo. Okay, how many blues we got? We got 2, 4, 6 blues. I definitely want to participate. Where's me? Okay, here I am. I got 6 blues. And 2, 4, 6, 8, 10, 12, 14 browns. And 2, 4, 6, 8, 9 greens. I love watching all the data pop up. 2, 4, 6, 8.
I know. I was saying, like,
Is yours not like the snack size?
No, I got a bigger one. They didn't have the snack size, so I got a bigger one. I'm sure everybody who bought their own probably also got a bigger one, but it shouldn't matter because it's the proportions, not the total number, right?
True.
Assuming that M&M's makes like the same number of colors and then mixes them all up and throws them into bags, whether you got a big bag or a little bag, it should be roughly the same proportions, right? Right? Small sample sizes, however, tend to be skewed just by chance. So you might have a bag with 0 of something. Could happen, which is why we're going to combine all our data. Let's see, where was I? Oh yeah, orange. 11 oranges and 8 8 reds and only 5 yellows. Oh, I think the brown ones are the most delicious because chocolate. Now we need to add another column here. We need to add a column to sum them up. Oh, we got to sum them up down here. That's right. I got to sum them up down here. Equal sum. And here we go. Total number of blues. Total number of browns, greens, orange, reds, and yellow. Yeah, we don't need the sum here, actually, you guys. We don't need that sum. That was my bad. We need the sums down here. These are the totals of all the colors. Right away, there's some differences. Isn't that interesting? Look how many blues. Look how many blues. Who's missing here? Ariel, where are you? We need your delicious data. Shelby, what happened? Come on. Okay, we got almost everyone here, though. It looks like everybody's there. Awesome. So real data, real experiment. We're going to find out something about the world here today. What we're going to do now, take these numbers, right? I'm just going to copy them and then go over to the R, go over to R. And at the top of this R script, we see that it says part 1, the observed counts, that's us observed. We want to put the count of blue, count of brown, count of green, count of orange. Oh, if you can't see everything, go to code, soft wrap long lines. Click that and it'll wrap it around so you can see everything. Okay, so I'm just going to select all this and then paste in those numbers. Now that won't work exactly because we need commas between the numbers. So I'm just going to put a comma in between each of these numbers. And then there's the data. There's our observed data. Easy, right? You run that line and right away you see over in the upper right-hand corner, you see observed. There's our vector of numbers. There's our vector of numbers. That's it. 103, 63, 98, 75, 69, 54. So we all got, right? Should be. Then to run the chi-square, all we do is this next line, which is just chi-square.test with our observed data, that little vector that we created. And it's going to store the results into something called result 1. So run this line by just making sure your cursor is on that line and hitting Control Enter. And now we see that we have created this object here with the results. And if you hit the drop-down menu here, you can see, oh, look, we've got all these different things stored inside of this result 1 object. And if we want to look at the results, we run this next line, result 1, and down here on the console window, we can now see our chi-square results. Cool, right? Easy. How's everybody doing with that? Good? Good, right? Nice. All right. Now what we just do is we can just take these results and just copy them from the console, go back over to the lab handout and say, okay, what are the results? Well, they're right here. Here they are. Just paste that into the table with the results. There are our results. Our chi-squared value is 26.086. Our degrees of freedom is 5. And the p-value is super duper little. Much smaller than 0.05 because it's e to the power of -5. That's really, really small. It's like 0.000008,587. Right. So do we reject the null hypothesis? Yeah. Yes. We reject the null hypothesis. Reject the null hypothesis. And what can we conclude about the color proportions of M&Ms? Yeah, that's right. They're not equal. They're not equal. The color proportions of M&Ms are not equal. And then you open up your parentheses and you basically put your results down in here with just a little bit of modification. The chi-square doesn't need that many significant digits. You can just put 26. Degrees of freedom 5. And for p-value, everybody pay attention. I don't want to see this as your p-value. That's not a very professional way of doing it. Instead, put less than 0.0001. Okay? I don't need that exact p-value. I just need to know that it's very small. In some cases, the exact p-value might be important, but here it's not.
Instructive.
Everything okay, Michelle?
Yep, it just gotta move you around sometimes.
Okay.
There you go.
All right, great. So that's our first test. What about the next test? The next test, part 2, we test for expected proportions. I went online and I found this.
Can you go back up?
So now I'm back to this.
Yeah, there, thank you.
The color proportions of M&Ms are not equal. Right? Straightforward. Chi-square is a nice, easy test. If you're not sure about how to state it, you could go over to the textbook and you could look at the chi-squared hypotheses and see how it talks about them. Chi-square hypotheses. I think it was the goodness of fit hypotheses. I just do a search. That didn't work. I maybe it was goodness of fit hypothesis. Or hypothesis for goodness of fit. I actually took notes on it earlier. Hypotheses for goodness of fit. That's what it was. That's where I found it. Okay. Hypotheses for goodness of fit is right here in the textbook in chapter 21. And it talks about how to state the null and alternative hypotheses. The null hypothesis states that all probabilities are the same on all days, right? That's from the day of the week and number of births example we did on Tuesday. And then the alternative hypothesis is simply saying that HO isn't true, right?
Sorry.
All right, great. So that's our part 1. Part 2 is to test for the expected proportions. And again, I went to the internet and I found this graphic that was showing different colors of M&Ms, because even though I thought I was being really creative with this idea of having M&Ms for the chi-squared lab, turns out I'm not the only super genius in the world, and other people have already thought of it and used it too. So they published this M&M color mix graphic from PBS, and here they found that they had 13.1% red, 20.5% orange, and so on. So this is apparently what the M&M company says it's supposed to be. Okay, well, is that what we got? Is that what we find? I don't know. Let's see. So I'll close this out. And if I can get to it, there we go. Bye. Back to our lab handout. We want to test for the expected proportions. So our question that we're trying to answer is, do our color proportions of M and M's match the proportions stated by the company? It's kind of like that one-sided t-test when we were comparing to a known population, right? Except here we're not comparing means, we're comparing proportions. Do our color proportions match? And so our null hypothesis is that the color proportions, we can just simply say it do not match those stated by the company. And you could be more specific and you could say probability of blue hypothesis. Okay, so probability of blue is 20.7 and probability of brown is equal to 12.4, et cetera, right? You could put that all out and state it very specifically. If you were publishing this, you would definitely want to do that. And your alternate hypothesis is that the color proportions of our sample do not match, right? They're not equal, right? There is a difference, those stated by the company. Cool. Right? Not equal to. We can copy and paste this code into R, or I think I might have already put it into the code here for you. I think I put it into the code here for you. So in part 2, yeah, I put it in there for you. I put the expected proportions and I translated them from percentages to decimals. So if you run this line here, just put your cursor on it and run it, you now have created something called expected P, and your expected P is just a vector of these proportions. And now to run this, oh, this shouldn't be result 1, this should be result 2, but I guess that's not going to hurt anything. Our result 2 for this chi-square test, we have the observed and we have P is equal to our expected P, right? We have the second argument that states the expected proportions. Run this line, and to see our result 2, copy and paste that down onto the bottom or type that in there, and then run result 2. And here down in the console, we get the chi-square test results for part 2, expected proportions. And you can just copy and paste that right over into the handout. What are the results? There they are. Those are the results. Our chi-squared value is about 8, degrees of freedom 5, and the p-value is 0.0135. So we found out that the proportions are not all equal, but are they the expected proportions based on what the company was trying to do? What they said they should be? Well, do we reject the null hypothesis? No. No, no. We fail to reject. We fail to reject the null hypothesis. We fail to reject the null hypothesis. And so our conclusion is, do the color proportions of our M&Ms match the proportions found by previous researchers or by the company in this case, because it was put out by M&Ms? Oh, I mean, yeah, they do. They match. We have no evidence to support the idea that they're different. So as far as we know, we can say all evidence points to the color proportions of our sample matching the expected proportions. Now, remember, we're not proving anything. We really are just saying we don't have evidence to say otherwise, right? Our chi-squared is 8.3. Again, I would, just include a couple digits. Degrees of freedom 5. P-value here, we should have the whole p-value because it's not a really small number. There's our exact p-value. Or another way of saying it is, again, we could say we have no evidence to conclude, we have no evidence to conclude that there is a difference in proportions. Difference in proportions. Just another way of saying it. Remember, we're not able to actually prove it. We're just saying that we can't reject the null hypothesis. Would more data change our minds? Possibly, but based on the sample that we have, we're going to have to say, well, looks like M&M company put out this proportion of M&Ms, color proportions, and this is what we have. So they meant to do that. More blues than browns. Right? That's what we found. More blues than browns when we look at it. Part 3, now this is where we get interesting, because the part 3 is where we do the two-way test to compare our class data and data from last semester's class. Actually, I thought the other two ones were interesting. Like, we now know that the color proportions aren't equal, and the M&M company does that on purpose. Now we can see if our sample is like last class's sample. And this will help you a lot with your homework because it's kind of similar, right? And I've given you the code. Question. You can write out the question in the way that makes sense to you. To me, it makes sense to say something like, do our color proportions of M and M's match those of the last biostats class? And here, notice I made it non-specific as to which semester, because I understand in the homework, I said that the last class was spring and this class is fall, but actually the last class was fall and this class was spring. So I'm sorry I switched them. Oops. Null hypothesis. Null hypothesis. Here's a little bit different. The null hypothesis is stated a little bit differently. Here we're really trying to say, well, is there a relationship or an association between the color proportions found this semester and those found last semester? Is there a relationship or association between the M and M color proportions found this class and last class? And if so, it might just indicate that there's like something going on, right? There's like not a difference in how they are and how they wait. Oops, sorry. I'm stating this as a question. I need to put this as a null hypothesis. This is really still another way of putting the question. All right, null hypothesis. Null hypothesis, there is no relationship or association between this class's color proportion of M&Ms and the last class color proportion of M and M's. And if you want to state that in a way that is more elegant, feel free. There is no relationship. Okay, and then you would just say the opposite is there is a relationship or association. Another way of saying that is that they're not independent. Are the proportions independent from one class to another? Or do they depend on each other? Does one affect the other? Now, again, let's go over to our R. And here we go to part 3. And I already put in the data for you in the observed last class vector. So just run that and you'll create this vector called observed last class that has the colors from last time. And here, let's make the labels for the M&M colors. This will help in our graphing step later. Now, it's a little more complicated to run the chi-square analysis with the two-way table. We need to create a contingency table with both row and column names here. Well, we don't have to include the names, but it's nicer again for later on when you want to look at it. So what we do is we create a matrix. We create a matrix. And that matrix is a combination of the observed, which is this semester, and observed last class, last semester. And then we have to state how many rows. We have 2 rows. And by row equals true. And the dimension names are a list that include this class and last class and the colors. If we run this line and then the next one, then down here in the console, you'll see we now have this little data table that has the colors blue, brown, green, orange, red, yellow, and this class, last class, right? This is our chi-square matrix. Here's our data. Then to perform the chi-square test of independence or association, it's just as simple as the previous test. The very first one is chi-square.test on M&M data. Just that. Run that, and then to view the result, we can say print result 3. And down here we have our lovely results, chi-square. Again, we can copy and paste that into our lab handout. What are the results? There they are. There are the results. Our chi-square value is 71. It's really high. And the p-value is much less than 0.05. In fact, we're going to get rid of this number and just put 0.0001, less than 0.0001. So do we reject the null hypothesis of no association? Yes, we reject the null hypothesis of no association. Yes. Great. Now, how do we write our conclusion? Is there an association between the color proportions of M&Ms found by us and by the previous class? Yes. There appears to be an association between the color proportions of M&Ms found by both classes. And here again, we want to state our evidence, our supporting evidence, which is our results again, less than 0.001. Open parentheses over here. But let's graph up the data, and that'll help us to examine a little bit more about what's going on here, right? What's associated with what? Go back over to R to make the graphs. And I want you to pull out some information from these results. And one of the things I want you to pull out from the results, which you could also do up here, if you look at in the results 3, you can see there's all these different parameters that come out of the results. You get this test statistic, you get the parameter, you get the p-value, the method, the data name, you get the observed, expected, residuals, standardized residuals, all this, right? And so the observed values can be pulled out of the results by saying result 3, that's the object name, right? $, which says in this column, observed. And you can see, oh, look, those are the observed values. That's exactly what we told it to be. It should match exactly what we got, what we put in here in our M&M data. Yeah, it matches, right? Just so you can see how to pull this out of the results. We can also look at the expected values. The expected values, and here I decided to round the results. So I just said round, and then result 3 $, expected, and then comma 2, that means round to 2. If I ran just this section, result 3 $, expected, I'd get this table here, which looks fine. And you might have already considered how this could be particularly useful for you when you're doing your homework. If you want to get the expected counts, hint, hint, you can use this, just put in the data for the homework into a matrix and get R to tell you your expected counts, and you can fill in everything without having to do anything with your calculator, right? But here I did the table. And so here are our expected counts. So if everything were equal, if there were no association between, if the proportion of blue M&Ms in this class and last class were the same, and it's hard to compare them because the numbers are really different. You're like, well, there was 105 blue this time and 22 last time. Huh? Okay. But last time, we would expect actually to have 83 this time and 43 last time. We would expect to have fewer blue this time and more blue last time. Something's going on. It's kind of a lot to look at all these numbers. That's why I kind of like to graph it up. Can we just go to the graphing? Oh yeah, one more thing. I want to show you this contribution. So another thing you can pull out of the results here are the residuals. And I think what this is, if I've got it right, these are the chi-squared contributions. No. Yes? Do I have that right? The residuals? Let me just double check that. Or is it the standardized residuals STR? All right, let's go to the graphing. So basically, though, what this tells you is this tells you the difference between your expected and observed values. So again, if you look at this difference between this is your observed value and this is your expected value, it's about 20 different. And if you divide that by the expected value, the overall totals, it should be 2.3539. And this is your chi-squared contribution. This is how much each cell is affecting the overall chi-square, I think. But then there's negative values. That's weird. Okay, you guys, I'm sorry. I'm gonna have to send you an email explaining this more because I was doing this right before class, and I'm not 100% sure that this residuals is the right residuals. All right, but we can still plot it, and you'll see it'll work. Okay, you need to install gplots. You need to install gplots. So if you haven't already, and this code got copied and pasted over kind of funny. So let's just install gplots over here. Let's go over to where it says packages and install, and then type in gplots, gplots. And you'll see here, gplots. Install that. There you go. Some red happens. That's all good. Once it's installed, you can run this line and that loads it. And then we need to convert the data to a table. So right now it's a matrix. We need to convert it to a table, and we'll call that DT for data table. And it looks the same. It's just a different format that R reads differently. I'm not really sure, just part of the code here. And then we can make a balloon plot here with the data table. And I think this is a really nice way of looking at the data. It's a really nice way of looking at the data, because it shows you the proportions. It shows you the proportions and how they differ in a very nice visual way. You can see there's a lot more blue this class than last class. The browns are roughly equal.
Yeah.
A lot more green this time than last time. And so it was sort of the blues, the greens, and the yellows that had really big differences. So,
One of those where it wants to be nice.
right, so those really big differences, that's
Okay.
what's mostly contributing to our chi-square,
We'll
our
actually
big chi-square. The next graph, we look at we'll load the library graphics, and that should be pre-installed. And then we can just make this mosaic plot. Make sure your window is big enough, you guys. If you've got a small laptop and your graphics window is small, it's going to show up looking all messed up. You got to make that graphics window bigger, and then you can actually see the plot. And it's a really nice plot. So this does a better job than, I think, a pie chart would, because we can compare the shapes of rectangles a bit better than the shapes of wedges. And we can see, so this is this class, this is last class, and these are the standardized residuals. So if you have an observed value that's a lot higher than the expected value, then it comes out as blue. And if you have an observed value that's a lot lower than the expected value, then it comes out as red, right? So bigger than 4 is blue, less than 4 is red. So this class, we had a lot more of the blues than expected, and a lot fewer of the blues in the last, a lot fewer of the blues in the last class. And so these are really showing us like what's making that difference. Like the overall chi-square statistic just tells us something's going on, but it doesn't tell us what. It doesn't tell us how this class differs from last class, why there's an association going on, why like the colors would depend, the proportion of the colors would depend on which class you're in. And I still don't really know why. It doesn't sort of make sense to me. So I think, but they all came out of bags. But they were different. They were different. There's a difference in like the reds. There were a lot more reds than expected last class, and a lot fewer this class. And then the oranges were roughly the same. The yellows were roughly the same. Nothing much going on, but you can see these bigger differences. So again, the surface of the element reflects the magnitude of its value. So the bigger boxes have bigger values, and the different colors show how different those values are from expected. Neat. Okay, now I gotta Google this this residuals, because I'm honestly not sure if the residuals is the right thing to be pulling out of the results or if we should be looking at the standardized residuals. Okay, so let me just go up here if I can look at it here and say ChatGPT in R, what are the standardized residuals from a chi-square test? In R, what are the residuals from a chi-squared test? Is that the contribution to chi-square? Is that what okay. We know, oh, it's explaining a lot. Well, that's good. Oh, I think it is. Okay. Observed frequencies. Okay, we know what observed frequencies are. Expected frequencies. Yes, we know what the expected frequencies are. We went over that. The standardized Pearson residual is calculated for each cell in the contingency table as R for residual is observed minus expected divided by the square root of expected. These residuals indicate how much each observed frequency differs from what would be expected under the null hypothesis given the sample size and marginal frequencies. Right. But that's still saying it's the standardized Pearson residuals where there's this other thing here called, you see, there's the STDRES. Okay, that's what I'm trying to figure out. What's the difference between this residuals and the STDRES, standardized residuals? Okay, so there are two components related to the residuals and the standardized residuals. Here's a difference. The residuals contain the standardized Pearson residuals. These residuals represent the difference between observed and expected frequencies, standardized by the expected frequency under the null hypothesis, as I mentioned earlier. Okay, great. The standardized residual contains the standardized residuals, which are also called Pearson residuals. They're computed slightly differently. Oh, they're computed just a little bit different in their computation. Okay. Okay. All right. Which one of these represents the chi-square contribution or chi-squared component as it talks about in the textbook? Okay, both. Both. Basically, both of them, the residuals and the standardized residuals, give us an idea of the difference in sort of the magnitude of the difference between the expected and the observed. So how much are these two things different? And that is what we're seeing here in the graph. Okay, great. That is what we're seeing here in the graph. So if it's bright red, it's saying these blue ones differed a lot between this class and last class, right? Because they're blue and red. And the browns also differed a lot between this class and last class. So we don't just know that there is an association, we can now hack into what is going on. We drill down in and look at that chi-squared contribution by looking at the residuals, and we can see, oh, here's how these color proportions differ. That makes sense to everybody? I wanted to walk you through my process of discovery as I figure this out. I think that's it. I think, oh yeah, you just have to copy and paste these into your, so if you say copy image, see if that works. If I copy that image and I go over to this table over here and I hit paste and it doesn't work, that's okay. Wait, look, you see this little drop down menu here, paste options, choose that picture. And there it goes. There it is. Great. Make that smaller so we can see both of them. Smaller, please. Make it smaller. Putting images in Word is often problematic. That's why I made a table with 2 cells to put them in there. Okay, then let's go back over to R. Let's run that first code for the balloon plot, which I just love. I love the balloon plot. I think it's so cool. It's just neat looking. And you can copy that image and go over to the handout and paste that in there. And again, you can make it smaller so it all fits nicely on the page. There you go. That's it. Save that and upload it to Laulima, and you have done your lab assignment for today. Okay, that's it. That's it. Save it. File, save as. I'm going to put it in my chi-square folder. I'm going to put my name on it just in case something happens. It's got my name on it. Save. Sure. There was an article that was written by a University of Hawaii student and myself a few years ago. And her name was Molly Murphy. She now works for BISC, the Big Island Invasive Species Council. And this is a paper that we wrote looking at the effects of feral pig damage on tree ferns in the wet forest of Hawaii. And if you look down here, the reason I'm pointing this out to you now is here we have the statistical analysis. And we used our old friends ANOVA with a post-hoc Tuckey's test. You remember this? And we also used the Fisher's exact test because it is recommended over chi-squared analysis when counts in any category are less than 5 in our studies. So this gives you a clue about some alternatives to use for chi-square. It's very similar to chi-square, but just more flexible for smaller counts. I highly recommend looking at this paper. I put it in your resources tab already, so you can read it if you're curious to see what other UH students have done in the past. And also how to use these analyses in real world data, just like ours. Any questions? We're here to help. Yes.
I was just gonna ask for Michelle. Sorry. So this is kind of what I was really about.
Have a great weekend.
Great for this one because I didn't know